We are now going to go back to the OSU enrollment data and try to find the best ARIMA model for this particular data set and then forecast future values. So just as a reminder to help set the stage here in terms of the story behind this particular data. So OSU has a particular office on campus that would make fall enrollment forecasts for each fall. And back in fall 2000, this forecast was 743 students too high. Now the reason why this was important is because based upon these fall forecasts, the university can then plan how much they expect to get in tuition dollars. And when they plan to have more students than would actually occur, then the tuition dollars that they get, of course, is less than what they would expect. And the university had a $1.8 million tuition shortfall, or at least that's what they called it, for the fall 2000. Now, this got me then interested in learning more about the process that this office uses for these enrollment forecasts. And they end up not using any kind of a ARIMA or SARIMA model at all. In the end, they use some very, we'll say, unsophisticated methods. But they do take into account some extra information, such as the number let me back up. They do take into account the number of students who are actually taking the ACT in Oklahoma. Why do they do that? Is because those students who are taking the ACT in their, let's say, senior year of high school, or maybe even junior year of high school, that can be used as a proxy to get at what you would expect for the number of students in Oklahoma who would go on to Oklahoma State University in the following fall. Also, what this office does is they use the on-campus sophomore, junior, and senior projections, or they forecast by class year based upon cohort survival rates. What that just simply means is, unfortunately, some freshmen don't come back to their sophomore year. Some sophomores don't come back for their junior year, and so on. So essentially, if they do come back, you have, let's say, survived. And so they use these survival rates based upon past experience to project how many will come back. Also, at this particular time, excuse me, the main campus at Oklahoma State University, which is located in Stillwater, Oklahoma, it's about a town of about 40,000, that's 60 miles north of Oklahoma City, 60 miles west of Tulsa. At that time, they were just starting to have integrate a new campus into their system, a campus in Tulsa, Oklahoma. Interesting side note, Tulsa, Oklahoma at the time was the largest city in the United States that did not have actually a public university in the city itself. And so that's why this was needed. And since this was just at the beginning stages, then in their projections, they used information about how many students were at Tulsa and basically expecting a 5% increase in students every year. Okay. Now, for my analysis here, what I'm going to do is use data up until the spring 2002 semester to simulate how one would get at a best model so that we can project fall 2002. Now, I know that this statement before that I talked about, that was an article in the student newspaper, talked about the fall 2000 semester. We'll come back to that to see how well our models would have approached that situation. But what I've what I'm going to do here is simply say, okay, let's say we have data up until the spring 2002 semester, and I want to forecast fall 2002 as much as how administrators would typically approach the problem. So I read in my data like usual, and then since spring 2002 goes up to time point 38, I take out time points 1 through 38 and put that into my object X. This is what I'm going to build my model upon. Then let's go ahead and find the autocorrelation plot and partial autocorrelation plot for this observed time series. And this is what we get. So we have evidence of non-stationarity in the mean, it looks like, because we have at multiples of 3. Remember, we have fall, spring, summer. So we have a season of 3. Excuse me. We have large autocorrelations that are dropping to 0 kind of slow. So what this is telling me is that I likely will have non-stationarity in the mean here, and I'm going to need to take care of that before I deal with anything more like with the partial autocorrelation function. Also notice, similar to what we've seen before, is that notice how in the off lag 3 multiples we have some large and absolute value autocorrelations as well. And well, why does this occur? Well, remember the fall semesters are going to be positively correlated with one another, but that fall semester is going to be negatively correlated with the spring semester or the summer semester as well because of that drop in enrollment. Okay, so what this is telling me then is to first take those first differences with respect to a season. So, and I should have brought this up before. Sorry. Now remember, if let's say I didn't need the seasonal differencing, and let's say maybe an autoregressive 1 model with respect to the season was appropriate, I would expect a large partial autocorrelation to occur at lag 1. Obviously, we also have lag 2 and lag 3 as well. And I would expect a tailing off to 0 at multiples of lag 3 for the autocorrelation function. And, perhaps these autocorrelations are actually dropping more to 0 at a faster rate than what we've seen previously when we had a non-stationarity in the mean problem. So what if we, let's say, went a different approach and said, okay, let's look at that autoregressive term for the seasonality and start there and see where that would take us. Now, I likely wouldn't have done that, but I think it's illustrated to see what would happen. And so I estimate my model the usual way. So for non-seasonality component, I'm not going to have anything there. For the seasonality component, I am going to have that autoregressive one with a period of 3. And so I estimate the model, put the results into a mod.fit type of object, but look what R gives me back. Error. It cannot estimate the model. And so what this is telling me then is that, hey, this doesn't work here. And you might be wondering, why is it giving me this kind of error? Well, remember, if we take a look at the differencing with respect to the season, that term is like saying, okay, capital phi is equal to 1. And so let's say if maybe capital phi was maybe 0.9 or 0.8, then it would not necessarily be unusual to perhaps see some of the stuff that we were seeing in that autocorrelation, partial autocorrelation plots. And so this is why I thought, okay, well, maybe let's take a look at to try to estimate the model without the differencing. But given that the model cannot be estimated, this tells me, okay, yeah, let's now proceed by taking a look at what would happen if I did do differencing. So to do this differencing then, again, remember I use the diff function. Here's my data in x. And remember, now I need that lag 3 because now I'm going to be looking at this, xt minus x sub t minus 3. I'm doing first differences. Going to look at the ACF plot. Going to look at the corresponding PACF plot as well. And this is what I get. So notice we no longer have those large autocorrelations at multiples of lag 3 in the autocorrelation function plot. So that's great. It looks like this has helped. Also, with our partial autocorrelations here, notice at lag 1, I have this large and absolute value autocorrelation. And perhaps what one could do is then interpret, so this is actually drawn at lag 1 here, interpret this particular value then as the first of the autocorrelations that are tailing off. I'm sorry, let me back up. I don't want to talk about that yet. Excuse me. So notice we do not have really any seasonal aspect here in the PACF. With the ACF, it doesn't really look like we have a seasonal aspect either. But we do have this large partial autocorrelation here. And so what one could do is look at the autocorrelation plot and see that, well, look, we maybe have like a tailing off to 0 there, suggesting that maybe I need a non-seasonal AR1 component in our corresponding model. Now, notice we have this kind of a wavy thing going there. That's not unusual to, again, find as part of this tailing off to 0, because notice how those waves are getting smaller. Now you might be a little bit concerned with, okay, that particular value is kind of large, is actually significant. And, you know, we'll talk about that a little bit more shortly. But I'm not really too concerned about that. You know, perhaps what this is telling me, I maybe need to add some kind of seasonal component, because notice this is at lag 9 where this is happening. But I would have expected to see something with like lag 6 and lag 3 if this were to occur. So we'll talk about that more later. Also notice here in these particular plots, these dashed lines, they're a little bit wider than what we've often seen in the past, and that's because we're only working with a sample size of 38 now. So when I take that plus or minus 1.96 divided by the square root of 38, I'm going to get a wider range there. Okay. So let's add then the AR1 term to the non-seasonal part of the model and see what happens. So to do this, I use my ARIMA function. I'm going to estimate the model. And I'm going to put a P here of 1. D and Q are 0. For the seasonal aspect, here's capital P, capital D, and capital Q. S is 3. So I go ahead and estimate the model. Here's little phi hat 1. Here is the sigma hat square W. And here is then the corresponding AIC as well. That will be helpful to examine later. Okay. Now let's actually use my examine.mod function to investigate the corresponding assumptions corresponding to our model, and also determine if maybe some changes need to be made to the model. So to do this then, I'm going to use examine.mod. Notice I put a max lag.20 there. Given our season's so small, I don't necessarily need to go up to a large number. Here's my Z test statistic to test whether or not phi1 is equal to 0 or not. And what we see is that we have a small p-value indicating that, yeah, this phi1 appears to be not equal to 0. Here are my corresponding plots that are generated by the function. Let me make this bigger. First, let's look at the standardized residuals here. Notice I'm at -2 to 2 here. We have no values, maybe one that's outside of -2, but this is not necessarily unusual because we would expect about 5% of them to be outside of -2 and +2. And we might have about 2. So I'm satisfied with these standardized residuals with respect to I don't think there's any outliers. Also, we don't really have significant trends in terms of large, let's say, sets of standardized residuals that are all positive or all negative. And so I'm happy with that particular plot. Now my ACF plot of the residuals, again, don't worry about lag 0 there. Don't even look at it. Notice how all the estimated ACFs of these residuals are within our dashed lines there. So I do not have sufficient evidence to indicate that any of the autocorrelations are different from 0. So that's good. My p-values for my Jung box Pierce tests, all of them are large. Again, this is good for this model. PACF, similar to the ACF, all the estimated partial autocorrelations are within those bounds. So this is telling me, hey, I don't have any additional dependence, it appears, left in my data that I need to explain from this model. Let's do a histogram of the residuals. I only have a sample size of 38 here, so it can be harder to assess normality with that small of a sample size. And while obviously we see some deviations there, I'm not necessarily alarmed by them from looking at this plot. The QQ plot, we do see some deviations as well. But again, with a sample size of 38, I'm not too worried. You might be saying, well, but look how far that is from that line. True. But I encourage you to try to simulate a few different samples of just from a normal distribution itself of size 38. Do QQ plots outside of the realm of time series analysis. And what you're going to see when you have that small a sample size, you're going to see some deviations, especially in the tails from that line. But in the end, since you know that you simulated the data from a normal distribution, that shows you it's not unusual. So when I have a smaller sample size like this, in comparison to other times where we have maybe a sample size of 100 or 200, I'm looking for, let's say, even larger deviations from what we would expect for normality in those particular cases. Okay, let me make this smaller again. So let's think about this now. Does this model make sense? Especially in terms of that autoregressive one term for the non-seasonal aspect. And hopefully the answer to your question is yes, this does make sense. And the reason why you should say yes is because, again, remember, we have students who are at, let's say, the university, and then let's say in the fall. And then in the spring, most of those same students will still be at that same university. And so it makes sense to have a one period dependence as represented by an AR1 for this kind of a setting. Some other notes here. Here's my corresponding results from the hypothesis tests. And I think overall, yes, I've talked about pretty much all these notes. Now, again, this could be my final model. And so if it is my final model, I need to formally state it as an ARIMA 100 by a 010 with season of 3. I can rewrite my model or write it out in terms of the actual form of the random variables as shown there. And of course, always remember to indicate what sigma hat squared W is. Okay. Now, what if I tried some other models? Where would that take me in this situation? So here's a summary of some of the stuff that I tried. Okay, so starting with that differencing with respect to the seasonality component. So remember that at lag 9, we did have that marginally significant autocorrelation. Well, so because of that, and since this is on my autocorrelation plot rather than the partial autocorrelation plot, I decided, well, what would happen if I added a seasonal moving average term to the model? So now I have a capital Q equal 1. See what happens. Well, this capital theta 1 ends up actually being significantly different from 0. Okay, that's interesting. The residual ACF and PACF plot indicate, well, maybe I might also need to add a phi 1 and theta 1 to the model. But when I do add that phi 1 to the model, now this capital theta 1 has a p-value now that's only marginally significant, about 0.11. Although the AIC is 516, which is a slightly lower than the actual model that we had found previously. Not much, but it is. So, maybe that might be a better approach, but, given that p-value there, I'm hesitant to use that model. Now, when theta 1, though, is added to the model with capital theta 1, capital theta 1 is no longer significant at all. And we also have problems with our autocorrelations as found from the Jung-Box-Pierce test. So I would not want to use that particular model. Now, another alternative approach is that, let's say, because there was a significant autocorrelation at lag 1, I decide to start with adding a moving average term for the non-seasonal component. This term is significant in terms of the p-value small, but the Jung-Box-Pierce test results in smaller p-values than what we had previously. Also, the corresponding model's AIC is 519.2, which is larger than what we had for my originally chosen model. Now, when both theta 1 and phi 1 are in the model, theta 1 is no longer significant too. So I don't want to go that route. Another alternative approach is, let's take a look at adding an AR seasonal component, so a capital phi 1. When one does that, it's marginally significant, p-value 0.086. Residual ACF and PACF indicate that changes still need to be made to the non-seasonal part. When phi 1 is added, now capital phi 1 has a p-value of 0.15, unfortunately, and little phi 1 is highly significant. The AIC, though, is a little bit lower, 0.02 lower than the actual model that I had previously chosen. So there are obviously other possible models that one could choose, though I'm happy with the model that I did choose. Now let's take a look at a plot of the first differences with respect to the seasonal component. This is what we get. Now, part of the problem here is we only have we only had 38 observations to begin with, and because of taking the first differences with respect to season 3, we only have 35 observations now that are plotted. But, it looks like maybe there is some kind of trend. And if there's that trend there that says perhaps I have non-stationarity in the mean. So another approach that one could follow is take first differences with respect to the non-seasonal component with also the first differences of the seasonal component. When one does that, this is the actual plot that we get. And overall, from what comparison to what we've seen previously, it looks like I don't really have any problems with non-stationarity in the mean. Here's an ACF plot and a PACF plot of the corresponding data as well, of the difference data, and we have no significant values. Now, one thing that does concern me is that notice how almost all of these partial autocorrelations are negative. I'm seeing some trends here, and this is something we really haven't discussed before, but if you see stuff like this, this might say, okay, there's still some dependence that's left in the data that I'm maybe not accounting for. So also, one could do the Jung-Box-Pierce test here, and it does indicate some marginally significant corresponding lags. So now we have more evidence that perhaps there's still some dependence that's left. However, I tried a variety of ARIMA models with AR and MA parameters, and none of them really produce AR MA results that has significant parameters though. Also, I'm a little concerned about doing the 1 minus B differencing here, considering that when I did estimate the model with an AR1 for the non-seasonal component, I had a phi1 of about 0.7, which is different from 1. And remember our previous discussion about how that 1 minus B can be thought of as phi1 being equal to 1. Now, if I did a 95% confidence interval for phi1, look what happens. This is with my actual chosen model that I had before. I get 0.45 to about 0.95. So I'm kind of close to that borderline with a value of 1 there. So there isn't necessarily strong evidence that indeed phi1 would be 1 and that indeed differencing would be needed. Now I tried to add other terms to the model, and in the end I really wasn't getting anything that I was satisfied with. So at least for me, I think the best model is this ARIMA 100 by 010 with a season of 3. But the key is that I've went through this process, I've looked at alternatives, I have valid justification for my particular model that I chose, but I think also there's valid justification perhaps for some other models too. And whenever you're in a situation, let's say outside of this class, where you do need to pick one model, the key is you need to do this thorough investigation and attach your justification with it and make it one final decision. Okay, so let's take a look at now using this model to do forecasting. So I'm going to use the predict function once again. My object where my results for my model fit is in one of these mod.fits. I'm going to go 6 time periods ahead. So in other words, this will be for 2 school years ahead. se.fit equal true so that I can get some corresponding confidence intervals. I'm going to put the results into an object called for.mod. Here's what for.mod gives me. So for example, this first value would be for summer 2002, which I believe would be x39. Here's for fall 2002 as well. I can also find my corresponding predicted values for my observed corresponding part of my time series. Find 95% confidence intervals, much like I did before. So for example, here is x39 for the summer 2002. I get 8,909 students as my upper bound. For my lower bound, 7,490 students. Here it is for that fall 2002. That's going to be very of interest to me. So we can now do plots. And so what I decided to do was break everything up into the different seasonal components, since there was only 3. I'm not going to go through the details of the code here. Please see it on your own. Especially something to pay special attention to is how I approach basically putting all 3 of these plots into one plotting window by working with some of the par function in R that allows me to control the spacing of the plots. Also notice how I remove the x-axis time and just leave it on the bottom plot. Okay, so what we have here is in red, we have the observed values. Black, we have the corresponding predicted and then the forecasted values. The green dashed lines are the confidence intervals, and the blue triangles are what was actually observed for fall 2002 and also for summer 2002. Excuse me. So this is what we get. So for fall 2002, my forecasted value is actually less than what was actually observed. And we can see it looks like the model is kind of having problems getting up to what was actually occurring for this part of the time series right there. Notice also what's important is that the triangle is within my confidence interval bounds. So this is working as we would expect. Now for the spring semester, you can see how my model in black is getting at the observed values red in a much better manner than what it was doing for a lot of the later fall ones. And then here's the corresponding forecasted values and the corresponding confidence intervals. Now for the summer, again, my black is mimicking the red a little bit better. Notice for my black here, for my forecast for that first future time point, it's a little bit higher than what was actually observed for that particular summer, but still what was observed is within my confidence interval bounds. So I'm very happy about that. Now something else I think that's important in terms of from a practical point of view here. Look how wide some of these confidence intervals are. Let me actually come back up here. So for fall 2002, I am 21,455. And I'm going all the way up to 23,185. So about a 1,700 difference in number of students for these bounds. Is this too wide to be practical for actual use by the university? Maybe it is, because that is quite wide there. And why is it so wide? Well, one thing is probably because we have 38 time points only. If we had more, larger sample size, perhaps we could get more narrow. But then again, you might be thinking, okay, now we're going earlier than 1990 with this time series for prediction, and is really what was happening in the 80s, what was happening in the 70s, something that's going to help me predict in the 2000s how well this model is going to do. Now, another thing to also think about here too is that we're only taking into account in this particular situation just the past data points. But similar to how this Office of Planning was working at Oklahoma State, it was also looking at information, for example, of basically the number of high school students that were available that would go to college. Perhaps we could incorporate that into the model as well and in the end, have tighter bounds for these confidence intervals for the forecasts. In this situation, you would expect this kind of information to be available. Unfortunately, I do not have that information about the number of high school students. But if it was available, then you can use actually another type of time series model that actually incorporates that. And we will have another section about how to do that later in our course. But in many, many situations, though, you don't have that extra information, and you would many situations outside of enrollment here, where you wouldn't have that kind of information, and in the end, you only have to deal with just the past time points. And so that's why this course, or any time series analysis course, focuses on those kinds of topics rather than focusing on always incorporating additional information when, again, often it's not available. Okay. Now also, maybe what OSU could do as a conservative measure is that what they could do is use the lower bound of the interval as the prediction of the enrollment, because you wouldn't expect the actual future enrollment to be outside of the two bounds for that interval. And so that could be a more conservative approach. And that might work, but again, we do see a pretty large distance there. Let's see what it actually is. So the lower bound is 21,455. I predicted something about 750 higher in terms of the point estimate. Perhaps for the university that's too far. Maybe you might go somewhere in between there too. Because eventually you do need to have just one overall number, because you need to make projections for then the tuition dollars, and you need to make so that you can do it for budgeting purposes. Okay. Now another thing that I did was I looked back at the past estimates by this office at Oklahoma State. So they always release every year what their estimates would be for the fall enrollments. And so this is what their forecast was. I went all the way back to fall 1998. And then prior to fall 1998, they made that forecast. And then what was actually observed, I gathered that information as well. And I looked at, okay, well, what's the forecast there? So actual minus forecast. So one year they were 976 students too low. Another year they were 743 students too high. And this is the particular year that article in that student newspaper actually focused on. And this has a lot more, this causes the university a lot more problems than forecasting too low. Now, what would happen then with the corresponding ARIMA model in this situation? So what I decided to do was I say, okay, let's use information only up to the previous spring semester corresponding to what was in that row. So spring 1998, let's actually estimate this model using all the data to spring 1998 and get a forecast using the model. And so this is what I get, which in the end ends up being very similar to what the office had. Again, we are underestimating. Here's the corresponding confidence interval. We actually underestimated so much, the actual value was outside that. Then for fall 1999, I took my data all the way up to spring 1999, estimated the corresponding model here again, came up with then the forecast. And look at, I was off by 3 only for the point estimate. Of course, then the corresponding actual value was within inside that interval. Then fall 2000. This is again the year that the article in the student newspaper focused on. The actual enrollment was 21,252. That office predicted something that was 743 higher. But look at what my model does. It was off by only 5. That is pretty good. And you could see what the ramifications would have been for the university if they would have had to use my model versus using their methods. Now, that might all sound great and stuff, but do realize then when I do exactly the same thing for fall 2001 to 2002, my model is off. It is underestimating what that enrollment would be. So then how could we then measure overall how well these forecasting methods work? So what one could do is do like a mean square error, where simply I find these errors, I square them, and then I have only 5 of these errors, I take the average. So I divide by 5. And what do I get? This is what I get here. And you can see my model does result in a little bit smaller mean square error than what the model that this office on the campus actually produced. Okay, so there's essentially a top-down example looking at some real data to show you how one can use these ARIMA models in a very useful situation.